Okay, so I will be going over the quadratic formula derivation in these slides and introduction. Solving equations of degree 2 is very common. Quadratic formula is generally used for many problems in engineering, so it's going to be quite useful. And having a formula for all of this for solving these quadratic equations is going to be very helpful. And what is a quadratic equation? Well, it's an equation that is in the form of ax squared plus bx plus c equals 0. And what is the a, b, and c? Well, a, b, and c are real numbers, and a is not equal to 0. The a not equal to 0 goes without saying. If a was equal to 0, well, then what would you have? Well, you'd be reduced to bx plus c equals 0, and that wouldn't be a quadratic equation. Quadratic equation has to have x raised to the second power at a minimum. Okay, so an outline of what I'm going to be going over. Number one, I am going to be doing some general solving ideas for, like, why would you need this? Then I'm going to do a graphical representation of completing the square. Next, I'm going to complete the square, and then I'm going to give some examples of solving quadratic equations by completing the square. Next, I'm going to take the quadratic formula derivation from completing the square, and then I'm going to use some examples of solving quadratic equations by using the quadratic formula. And then I'm going to explain the concept of a discriminant, and then that will be it for the scope of this lesson here, the scope of these slides. So the idea, well, what's the idea? For an equation of the form ax squared plus bx plus c equals 0, what you want to do is you want to solve this equation for x. And you're going to need a systematic way of doing it. You don't want to sit there and guess at it all day long. I mean, you probably could do that with certain situations, but in general, you want to have a systematic way of doing it. You don't want to just sit there and keep doing trial and error. Computers usually use an iterative technique to give a very good approximation of this. So when you use a computer system or a calculator that's capable of solving a quadratic equation, what it usually does is it makes a very, very good numerical approximation of it. Some of them, some calculators can give you a symbolic output for it, and that's when you'll see symbols for irrational numbers such as square root of 2 or pi and things of that sort, instead of it just giving you a really good approximation. So they do have those types of calculators and computing systems, but usually you're going to get a very good approximation of it. So next, however, our systematic way will give exact numbers. So you're going to get things like square root of 2 and things of that sort. So it's going to get, this way that we're doing it is going to give you the exact answer. More of the idea. Okay, so if the left side of ax squared plus bx plus c equals 0 is a perfect square with a equals 1, it can be factored and x will be reduced to a power of 1, and this will allow us to solve the quadratic equation. So that's a requirement of it. The a has to be a 1 when you solve this quadratic equation by completing the square, because it has to be a perfect square, and that's a requirement that a equals 1. So completing the square is about reforming the left side to be a perfect square for factoring capability. That's basically what it comes down to. So let's go into the perfect square concept. So for a perfect square, we're going to start off graphically with the square itself. So you have this square, and then you have where you're going to divide it up into pieces. So you start off with a perfect square graphically, and you're going to divide it up into pieces there. And over here in the middle, this is still a perfect square. This is a square here. Obviously, these aren't perfect squares, and then we'll see the impact of that. So this side of it, it has a certain length. We're going to call that x. This side, it has the same length, so it's x. I just put extra notation down here on the bottom so that we know that this length here is equal to x, and this length here is equal to x. So next, if we want to figure out, well, what is the area in here? Well, it's going to be this one dimension by that one dimension, and then that's going to give us x squared. So next, down here we have b over 2, some constant over 2. So b is going to be divided by 2, and also over here, this b over 2 is the same as that b over 2 because this is a square. So this side is just as long as that side. And so just to put some notation over here, that means this segment here, this segment length is also b over 2. And then also up here, this segment length is also b over 2. So then I'm going to want to compute some areas here again. And so the square down here at the bottom is going to be b over 2 times b over 2 gives you b over 2 squared. This area here is going to be b over 2 times x. That gives you this area. And in order to get this area, it's going to be the same. It's going to be b over 2 times x. So you have all of these areas, and completing the square starts from here, and what you do is you add up areas. So it's based on areas. So you're going to take each one of these x squared, b over 2x plus b over 2x plus b over 2 squared. You're going to add them up. And so when you add them up, these areas from the graphic, you're going to have this. And so when you combine like terms, which is your b over 2x plus b over 2x, those are like terms. So you combine those, and then you end up with x squared plus bx, because you got half of b here plus another half of b that gives you 1b. So it combines to be bx there. And so that's what you have. You've combined all your like terms. So this is the final form that we need to have on the left side to have a perfect square, so that we can factor the left side into x plus b over 2, all of that squared. And that's really the main reason why you're going to complete the square. So as a summary point, by completing the square, you have a perfect square which can be factored. And this is the relationship here. So again, x squared plus bx plus b over 2 squared equals x plus b over 2, all of that being squared. And so it can be factored into that form. So let's use this in an example here. I'm going to use this equation here. I want to solve x squared minus 8x plus 13 equals 0. That's the equation that I want to solve. So let's use completing the square in order to solve that equation. So you reform it easily there, and you have your x squared minus 8x equals negative 13. A equals 1, so no additional adjustments are needed. Remember, we needed to make sure, before we did some completing the square, we needed to make sure that A was equal to 1, and it is in this example here. So no additional adjustments are necessary. So next, you go ahead and you compute b over 2 squared. And what is b here? B is your -8. So you're going to take -8, divide that by 2, all of that squared, and that's going to give you, it's going to collapse first into -4 squared, and that's going to give you 16. Now you want to keep that -4 squared and put that on to the left side of your equation, and you're going to want to put the 16 on to the right side. And you can do this because you're keeping the equation consistent and equal on both sides. You're not changing the algebraic statement itself by adding equal quantities to each side, even though those equal quantities don't necessarily have to be in the same form. So again, add the computation to both sides, and then you end up with this. So now with it like that, what you can now do is reduce your, add your like terms on the right side. That's going to give you 3. 16 minus 13 is going to give you 3. And then you're going to factor the left side, because the left side is a perfect square. And so when you factor it, it's going to look like this. And then when you simplify what you have, it's going to be that. Okay, so it's going to start off with x plus that -4, all of that being squared, and then when you simplify what's inside of those parentheses, then you end up with x minus 4, all of that being squared. So now when you have it in this form, you can solve it because x is to the first power, and it's now you can isolate x by itself to the first power. And so when you solve it, you apply a square root to both sides, and make sure that you have your plus and minus here with your square root. That is your algebraic rule for when you apply the square root. So then you transfer your 4 over to the other side. So your answer is going to be x equals 4 plus or minus square root of 3. So example 1, solution 1, check. So you have these two solutions here. Okay, you have x equals 4 plus square root of 3, and you also have x equal 4 minus the square root of 3. This is the reason why you need to have it as plus or minus, and you'll see how that works out as I go through a solution check for both of those answers. So one is going to be 4 plus the square root of 3. The other one is going to be 4 minus the square root of 3. I'm going to restate the equation just for reference, and I'm going to check x equals 4 plus the square root of 3. So what do? I put that in place of x in the original equation and check for consistency. So once you use your FOIL rule and you expand this, because you're going to expand all of these terms, and you're going to add the like terms and see if this equals 0. So once you FOIL that out, you have 4 times 4 equals 16. 4 times square root of 3 is 4 square root of 3. Square root of 3 times 4, that's going to give you 4 square root of 3. Last but not least, square root of 3 times square root of 3 is going to give you 3. And you're going to continue to expand. So you do that here with the -8 in these parentheses here. So -8 times 4 is going to give you -32. -8 times square root of 3 is going to give you -8 square root of 3. And you're going to add that to, your 13 just stays 13, of course. And so now this is in an expanded form, totally expanded, and you're going to add your like terms, and then eventually that reduces to a form where it's easy to see that it does equal 0. It's going to be a positive 32 here, negative 32 there, positive 8 square root of 3 here, negative 8 square root of 3 there. When you add that all up, of course, it's going to equal 0. So that initial check checks out just fine. So that has definitely been verified to be a solution of this equation. So next, the next solution check for the same example. Again, I restate the equation just for reference, and we're going to check x equal 4 minus square root of 3. And what do we have? We go through the same expansion process here, and when we expand and have everything where, we did this FOIL here, 4 times 4 gives you 16, 4 negative square root of 3 gives you negative 4 square root of 3, negative square root of 3 times 4 gives you negative 4 square root of 3, negative square root of 3 times negative square root of 3 gives you 3. And then you're going to expand this here with the negative 4 being negative 8 times 4 gives you negative 32. Negative 8 times negative square root of 3 gives you positive 8 square root of 3. And then so you just combine these like terms, and you're going to continue to combine. And at the end of this, it's going to be easy to see that 32 minus 32 is 0. Positive 8 square root of 3 minus 8 square root of 3, that's also a 0. 0 plus 0 equals 0, which is also equal to 0. And so that second solution checks out just fine. That's why you need to have your plus and minus sign there, because you have two solutions. Okay, so on to example 2 now. So I'm going to solve the equation 3x squared minus 12x plus 6 equals 0. And so we have 3x squared minus 12x equals negative 6. A equals 3 in this example. So I'm going to make an algebraic adjustment, and so divide both sides by 3, and then we end up with this. Next, I'm going to compute b over 2 squared. What is b? b is negative 4. So you have your negative 4 over 2, that being squared, and then you have your negative 2 squared is going to be equal to 4. Then you add that computation to both sides. When you have it, of course, again, in this form on the left side, then now you can continue on, and you are going to factor the left side, because it's what? It's in a perfect square form, right? Factor the perfect square left side, and then this is what you get. Simplify that to x minus 2 squared equals 2. Then you're going to solve and apply your square root to both sides, but use your square root rule, and you have plus or minus square root of 2 on your right side. Transfer your 2 over there, and so x equals 2 plus or minus square root of 2. So let's go ahead and check that solution. I'm restating the equation just for reference. And the first check that I'm going to do is see whether or not x equals 2 plus square root of 2. And so we put that in place of x, and so we have this. We use our expansion rules to expand, and then we have this. We expand some more by doing distribution there. So now that you're in this expanded form, combine your like terms and reorder your like terms so that you could easily see that all of this now equals 0, because 24 minus 24 is going to give you 0. Positive 12 square root of 2 minus 12 square root of 2, that's going to give you 0. So 0 plus 0 equals 0. So that's a true statement, and that all checks out good. So next, I'm going to restate this equation again, just for reference. Now we're going to check if x equals 2 minus square root of 2 is also a solution. So we put that in, and we use our distribution rules. We use FOIL and distribute that 3 in here, and so when we expand, we combine like terms and organize the left side. So reorder it, just organize it so that it becomes very easy to see that 24 minus 24 is 0. 12 square root of 2 minus 12 square root of 2 also gives you 0. 0 plus 0 equals 0. So that is a true statement, and that all works out. So next, we're going to derive the quadratic formula. So how do we do this? Well, we do this by using the technique that we just went over, which was the completing the square technique, to derive that formula for the roots of the general quadratic equation. So again, that general equation is your ax squared plus bx plus c equals 0. And the quadratic formula can be used to solve the quadratic equation that we have here. So let's go ahead and start deriving the formula. So we take that c and we take that and put it onto the right side, and then we're going to divide by a to ensure that the coefficient of x squared is 1. So remember, that was our rule that we had to go by whenever we're completing the square. We got to make sure that a is equal to 1. And so when we do that, then we end up with this. And then now we're going to add this term here, the b over a. We're going to take that term, we're going to divide it by 2, and we're going to square it. And then we're going to add that to both sides. But again, on this left side, we're going to leave it in this form here, the b divided by 2a, all of that being squared. We're going to leave it in that form. And then on the right side, we are going to have it in this form. So you're going to have unfactored form of it on the right side, and you're going to have a factored form of it on the left side. So again, you have your factored form of it on the left side, your unfactored form on the right side. Now, we're going to factor the left side since it is now in a perfect square form. On the left side, that's going to give us x plus b over 2a, all of that being squared. And so we have that now factored. Now on the right side, we're going to add the terms on the right side. And in order to do that, you have to have, of course, a common denominator. You have to have the same denominator in order to add these two fractions. So what I did here was I just simply said, okay, 4 times a squared times a, that's going to give me 4a cubed. This 4a squared is being multiplied over here on the left. This a is being multiplied by the b squared, and that's what you have here. Then next, what I did was I factored out an a from what I have, on the top of here in this numerator. I factored out an a, and then now as a factor here, I can cancel that with that on the bottom and simplify it more. So then I end up with this, and then I'm going to just organize these terms on the right side in the numerator. So that gives me this, the b squared minus 4ac in the numerator, and then I have 4a squared on the bottom. That 4a squared can be factored into 2a, all of that being squared. So next, I'm going to solve for x and apply my square root to both sides. And I'm going to have plus or minus b squared minus 4ac divided by 2a squared on the right side. And so then I'm just going to transfer that positive b over 2a to the right side, from the left side to the right side, and you're going to have negative b over 2a on that right side. Next, I'm going to continue to simplify here, and you have the square root, for all of this on your right side, but then that applies to both the numerator and denominator separately. And this is in a factored form where it's being squared, so that can simplify to 2a. And then when I combine the 2a here with the 2a there, that's going to simplify to negative b plus or minus square root of b squared minus 4ac, all of that being divided by 2a. And so that is it. That is your quadratic formula right there. So I'm going to use the formula now, and to use the formula, I'm going to first solve 3x squared minus 5x minus 1 equals 0 using the quadratic formula. And so in this example, a equals what? It's the 3, right? Equals 3. B equals negative 5. C equals negative 1. Now, the good thing about the quadratic formula is that you don't have a need to turn the a on the left side. You don't have to turn that into a 1. You have no need to do that because it's already built into the formula itself, because we did that when we derived the formula. We made sure that it was equal to 1. So that's already built in. You don't need to do that. You just need to apply the formula. So all you need to know is, well, what is A, what is B, and what is C? And in this example, A is 3, B is negative 5, C is negative 1. So next I use these values in the quadratic formula, and I just simply put those in place. And what do we have here? We have this situation where your negative 5 for B is here, and it's just within these parentheses. Same thing here with your b squared. You have a negative 5 being squared. Same thing with your negative 4ac. A is equal to 3. C is equal to negative 1. And down here you had 2a. A is equal to 3. And so after you apply it, you simplify, and this is the answer that you get. So x is equal to 5 plus or minus square root of 37 divided by 6. And just make a note that you have two solutions. Okay, so you got two solutions for this one. You don't always have two solutions. And so we'll see with more examples what are the other cases that you could have. So I'm going to use the formula to solve a different equation. 4x squared plus 12x plus 9 equals 0 using the quadratic formula. Oh, and by the way, you should do a check to make sure that all checks out and makes sense for you. I'm just going to skip the check so I can just keep moving on into the lesson, but I'll leave that up to you because we did go over some checks previously before with the other ones, and we definitely now know how to do that, so I'll leave that up to you. But with this next problem, okay, so I'm going to solve 4x squared plus 12x plus 9 equals 0 using the quadratic formula. So what is A? A is 4, B is 12, C is 9. And you just simply use those values, your negative being applied to your positive, 12 for B, and you have 12 being squared here and so forth. And then you just simplify that, and then you are going to end up with 144 minus 144 in that square root. It's going to give you the square root of 0. Square root of 0 is simply 0, so you end up with x equals negative 12 over 8. That can be further simplified in lowest terms to negative 3 over 2. So notice that there's only one solution with this problem. It's not a plus or minus sort of a situation where you have two solutions. you only have one solution here. So next, I am going to solve x squared plus 2x plus 2 equals 0 using the quadratic formula. So I'm solving this quadratic equation using the quadratic formula. And so a equals 1, b equals 2, c equals 2. And so use those values in your quadratic formula, and you end up with this case. And you simplify even more, and then you're going to have negative 2 plus or minus square root of 4 minus 8. That's going to give you a negative 4 underneath your square root here. And so you keep simplifying that, and so you have square root of negative 1 left in there. And so you really can't go any further than that except to just simplify things just a little bit more by taking this and turning it into this. So you have this one single denominator there that can be split up as a common denominator, and then that can simplify more to this because you have these two factors here on the top that cancels out, and then you have your negative 2 divided by 2 that gives you negative 1, and so it reduces to this. Now there's one thing that you have to take notice of here, that there's no real solution because the square root of negative 1 is not defined in the real number system. In the complex number system it is, and you'll be able to use that, in the complex number system. In fact, in the complex number system in math books, the square root of negative 1 is notated as I. So wherever you see I in a math book, that's in the complex number system, and it means the square root of negative 1. In the electrical engineering books, instead of using I, they're going to use J, and that's simply because they use I for current in the notation of electrical quantities in electrical engineering. So they just use J, but it means the same thing. It means the square root of negative 1, and you'll need to use complex numbers very, very frequently in electrical engineering. So at this point in our slides here, it is called a non-real solution. So you do not have any real solution. It's not to say that it's not a solution. It's just to say that it's not a real solution. It's a complex valued solution. As an assumption, we're dealing with the real number system. So in the real number system, we call that a non-real solution. So the discriminant, the quantity b squared minus 4ac that is under the square root sign in the quadratic formula is called the discriminant d of the equation. It's under your square root sign. And so again, the d equals your b squared minus 4ac. Now we saw that there are three possibilities and consequences of d. So number one, d can either be greater than 0, and the consequence of that is that you have two distinct real solutions. The second possibility is that d is equal to 0 and you have one real solution. Number 3, d can be less than 0. You have no real solution in that case. So that's basically the idea of a discriminant, and you can use your discriminant to figure out in advance whether or not the problem that you're dealing with has two distinct real solutions, one real solution or no real solution. And that's just a kind of like a diagnostic sort of a thing that you can use as you solve quadratic equations. And it's good to know that, so that when you do get an answer, you know whether or not your answer makes sense based on, your discriminant that you calculate first. So that's basically it. That's the concept of the discriminant. that is the end of my slides on this particular topic of the quadratic equation and the quadratic formula and completing the square. So hopefully this was helpful to you. Thank you for watching and have a nice day.